Hello there and welcome to the iRevise supplementary series for A-level physics. In this short video we'll be taking a look at capacitors. We will not be covering anything like the basics of capacitance, two plates, series and parallel circuits, these types of things. But what we will be looking at is charge and discharge graphs, which are done in some curriculum, not in others. We'll be looking at maybe some of the equations of the charging and discharging. We're looking at graphs for the voltage increasing and or decreasing depending on charge or discharge. We'll look at the current increasing or decreasing. We'll be looking at time constant, any calculations involving more in-depth formula for the charge and discharge. That's the main purpose of this video. We might see the odd question reviewing some of these things that are basic to all curricula. Not all A-level courses cover capacitors the same way, but I've got some questions from AQA, OCR, Edexcel, WJEC, Cambridge, Pre-U, and all of that stuff in this video. So let's get on with it.
Okay, and before we start any questions, what I'd like to do is just talk to you about the charge and discharge questions for the capacitors. You might note that the discharge equation looks very similar to what you might see in your nuclear physics unit, where again you have some sort of exponential there. Now whether that's number of atoms or isotopes, I should say, or or the activity, you're going to have this negative something. Maybe there's a lambda here, or there's this RC, which is the time constant, but it's a to the power of negative t. And let's just take a look at how that graph would look. Okay, so you'll start off. Remember, in the equation you've got some sort of multiplying factor out in front. That's fine, but just a real basic graph. If you've got e to the 0, the answer is 1. That can be multiplied by whatever it is. Okay, so if the charge is a certain number of coulombs, or your charge-discharge questions, or with some of your capacitor questions, sometimes there might be a voltage out in front. There might be the current. Okay, now you can see how those might relate later. Okay, but the point is, you're going to start off at a certain amount, and then you are going to deteriorate. Okay, and so it's going to go, as time increases, you've got e to the negative, and it's going to be a very, very, very large number, which makes it a very small answer on the y scale. Okay, that's for the discharge. If you look at the charge formula, it's a 1 minus that. Now let's just take a look at what that really means. If we're here at time 0, well, we know that 1 minus 1 is going to be 0, so we can expect the charging graph to start at 0. We would expect the charge across the capacitor to start at 0. Okay, and what would happen is, as this number gets closer and closer to 0, you're going to have 1 minus 0, which is 1. And so you can see that graph, this is the charging now. Okay, so the orange is the discharge, the red is the charging. The charging is only ever going to get to a maximum amount. It has to level off somewhere. Okay, and so that's what happens. Right, so this is an OCR, Exploring Physics, Physics A. We've got a capacitor being charged through a resistor. They're asking us about what the equation would be here. Okay, so the EMF is 150. Negligible internal resistance. The time constant is 10 seconds. Okay, so that means R times C is equal to 10. All right, now remember our formula was negative T over RC, so that's going to be negative 0.1 T. So we've ruled out C and D. It's either choice between A and B. Now they're talking about the potential difference across. Okay, so if the potential difference is 6, we can have an equation, because here's an EMF. We can have the equation in terms of the potential difference. All right. So here we have an equation in terms of the potential difference. That's how it would be. And so I think we see that if V naught is the actual full EMF, that I think A needs to be our answer there, because 0.6 volts is the voltage across that resistor at that time. Right, so remember that if this is the equation for the charging of the capacitor, okay, or what's the change in voltage across the capacitor, then what's it going to be across the resistor? It's going to be the opposite. It's not going to be the opposite. It's going to be what adds up to the all right, so it's going to be what adds up to the 1.5. So if you've got the equation of the 1 minus that e to the negative TRC, that's what it would be for the capacitor. Therefore, what we're subtracting from that 1, from that 1.5, this is the equation for the voltage across the resistor. Okay, the two should add up. I think you would see here that if we took 1 minus e to the t negative t over RC plus e to the negative t over RC, if we add these up, they cancel out to 0. We're left with 1. That's the 1.5. That's the total. So that's how you want to look at those questions. Let's move on to 14. This time we've got a capacitor being discharged through a resistor. So for the discharge, we know that the voltage across the capacitor will be of this form. So for the resistor, it's gonna have to increase, because there won't be any voltage across the capacitor. It'll all be across the resistor. So let's see the capacitor here. Okay, so again, the time constant's 0.1. What do we got here? What's happening with the current? Well, at the beginning, when we close the switch, the current will be a maximum because it's discharging. So again, we rule out C and D. And what are we going to have? Well, are we going to have at one time constant it all the way drained? No. The time constant is the rate at which this charge is going to kind of leave or enter the capacitor. And so I think we're going to have to go with B here. And also this number, this 37 here, if we were to... So what did we have here? Negative 0.1 to the t. So they're saying at 10 seconds. So what's 10 times 0.1? Well, that's e to the negative 1. And I think if you take your calculator and you go e to the negative 1, you'll find that you get 0.367. So we'll round that up. We'll round that up to 37% of the original charge, or in this case, the original current. Current is the rate of flow of charge, so that's fine. Okay, so I hope that makes sense. You will have seen that number when you've talked about time constants and this sort of thing in your class. All right, so moving to take a look at the answers real quick. We were doing questions 13 and 14, and we said A and B, didn't we? Okay, next I've got an OCR. This is a Physics B. This is the Advancing Physics Literacy in Physics. Question 2, we're going to charge a capacitor in a circuit with 2 resistors in series. Show that the potential difference across this resistor here, the 4.7 kilo ohm, is about 4 volts. Well, this is a potential divider question, but we can quickly do it just to kind of... So what we would have here is we've got a combined resistance of 6.7. If I want to figure out what the current is, I'll do the total voltage over the total resist. I'll do 6 over 6.7. So I'll get a current of 0.89, whatever, and then we are going to figure out what the voltage is across that 4.7 kilo ohm resistor. And so we'll take that answer there, and we'll just multiply it by the 4.7. And so I get 4.2, which is roughly 4 volts. Okay, let's move on and see what they're asking about with part B. This time the time constant is 15 seconds. So here's what we have. Show that the time constant is 15 seconds. Oh, I mean, time constant is RC. So the total resistance was 6.7, and we're going to go times, I'm going to do 2.2. Yeah, so this is 2200. 2.2 times 10 to the 3 microfarads, so that's 2.2 times 10 to the negative 3 farads. And this is kilo ohms. So that's 6.7 times 10 to the 3. So those exponent bits will cancel out. 6.7 times 2.2 gives us 14.47, which is approximately 15 seconds. Remember that it's very important to show the calculation, get the calculator answer, and then say, yeah, that's roughly 15 seconds. Or you can just leave it like this and say, yeah, it's this many seconds. The worst thing you could do is punch it in your calculator and say, yeah, that equals 15. You won't get the mark for that. I know different exam boards can be picky about this, so just watch it. I would not do this. Make sure you plug out an unrounded answer and then say, yeah, see, close enough. Okay, so on to part C. We've got a graph here that shows the potential difference across the capacitor, and it goes up to 5 RC. Remember, RC is the time constant. We can talk about that. That's 5 time constants. Like you might talk about how many half-lives in a graph, and this is how many time constants. They want us to add a line for the 4.7 kilo ohm resistor, and if I can switch colors, for the 2 kilo ohm resistor. Okay, so remember that for the charging, when we have the charge, that the voltage across the capacitor is this equation, this 1 minus stuff. But because we're talking about the voltage across, or the PD across the resistor, we're going to be using this equation here. And since we're counting in time constants, it's nice and easy. We'll let T equal RC, and we know that that should mean 37% of the original. So if I take 37% of 4.2, I get 1.6. So at one time constant, I should be roughly at about here 1.6. All right. Now we know that this should curve nicely. I'm only going to do the one. If you want to plug in those numbers, you can. But I think we just need a graph that will kind of drop down like that. It's not the perfect thing. I'm on a tablet, but I think you could draw something better by hand. Let's, of course, we'll label this. This is the 4.7 kilo ohm graph. I'm not sure how you label these. We'll just say it's the larger of the two resistors. You could say, hey, let this be R1, let this be R2. You could just label them R1 and R2. Maybe that's better. If I take 37% of the, what's it going to be now? 1.8. What did I say up here? Yeah, it's going to have to be 1.8 for the smaller one. So 37% of 1.8 is going to give us 0.666. Even round, that's creepy. So I'm here about 2/3 up, and I'm going to start here 1.8, and I'm going to go down. Now these probably I probably should not cross. I've drawn this a bit sloppily. Probably at some point they will both approach 0, but I think they're crossing way too early here. This blue line should be above the red there. Okay, so maybe draw your smaller value line first would be my advice. Okay, we'll move on. Calculate the time it takes from the start of the charging for the PD across the capacitor to reach 5. Well, we know the PD across the capacitor is this equation here, right? We know that this is going to start off at 6. We want to know when it's going to equal 5. Okay, and there's a minus here. Okay, so we'll do a 1 times 6. We'll also have a minus 6 e to the t RC. So we are looking for when t to the RC is going to be equal to 5/6. We'll divide every term in that setup by 6. Okay. If we take the ln of both sides, so we'll have the ln of 5/6 is going to equal negative t over RC. And what we can do is we can take that the time is going to be negative RC times ln of 5/6. And so ln of 5/6, because it's less than 1, is going to be a negative number, so it's going to balance out with that negative there. But so far we've got negative 15 ln 5/6. Let's give it a try. So 5/6, we'll take ln of that. Yeah, it's a negative number, and then times 15, and we're going to get 2.73 seconds. Let's have a look at our answers and see how we've done here. Right, so 4.2 across, simple potential divider, that's fine. We did do it because we needed to use it later on. We figured out it was close to 15 seconds. That was fine. The graph You don't need to plug in all the values. They just say start at the value of 4.2, which is what we calculated up above, and exponentially by I, decreasing down to 0 by 5. Okay, so we've got to make sure it's done by 5. I kind of flattened it out, and I don't know. Maybe my blue line probably should be a little bit better. I think it leveled off much too quickly. Probably if I had a piece of paper, I would rotate it upside down, and I would draw my curve kind of with my. It'd be easier to draw that curve, I think, because you're coming in from the top. It's easier to draw a curve like that. Okay, so that's how I would handle that. And then the same thing. It's a more shallow curve for the red line there, but again, same thing. It needs to be reaching 0 at so I'd say we got it, but watch your lines. Make sure they're a little bit neater than what I've done. And then did we get 2.27?
Did that go the way you thought it was going to go? Nope.
What's going on? 5. Oh, they 1 minus 5/6. Oh, yeah. Divide everything by 6. I get 5 over 6. 1 minus e to the TRC. I brought this whole thing to the opposite. Oh, so yeah, I should have. Oh, I forgot that bit.
Idiot! God, so stupid. What a dumb question.
1 minus 5/6, haven't I? Because I brought this over and I brought this over, but I forgot the 1. Watch that. So it's ln of 1/6. So it's still negative because it's still less than 1, but my number's going to be off. My number was off. And it's going to make things off. It looks to be like more like a factor of 10 type thing. So ln of 1/6. I think with enough practice, you recognize these mistakes. I haven't done this kind of stuff in a while. I think with enough practice, though, you recognize, hey, it needs to be smaller. So we'll do ln of 1/6, and when you do that, you get 27 seconds. Now, an alternative method would be to draw a horizontal line on the graph at 5 volts. And a vertical line to RC, you get a range of 1.7, 1.9. They expect you to get 1.8. So RC times 1.8. And you should get between 25 and 28 seconds. Well, I mean, look, this graph doesn't have many divisions here. I drew these in myself, and I would dare say this is a smaller distance here than this. It's not the perfect graph. But what they're saying is you take a line at 5, drawing it across, is that what they've said? Horizontal line and then a vertical line to RC. So we draw it across at 5 and then a vertical line to RC. When they say a vertical line to RC, they mean the RC axis is what they mean. So I'm not drawing a line to 1 RC. What we're doing is we're going to draw a line from where we've crossed here, and we're going to draw a line down. And this was a little smaller than it should be, moved over a little bit. So they say it should be in the 1.7 to 1.9 range. I would, if I make my 2R here, my 2RC here, yeah, I could say it's between 0.7 and 0.9. Even where I've drawn it very poorly here at the beginning, it still fits in. It seems a very imprecise way of doing it. But if you don't know the equation and you've forgotten it, then you can do it graphically. That's fine. Keep that in mind. Right, okay, so we've got an OCR. By the way, I didn't mention the multiple choice questions were from 2019, and the previous question was from, again, June 2017, just like this one, except this is a Physics A, United Physics. So we're going to investigate how the discharge of a capacitor through a resistor depends on the resistance. Okay, sure it does, yeah. Okay. And we've got them in parallel, therefore. And a student charges the capacitor of capacitance C and discharges the resistor of resistance R. Okay. And so the time constant The time constant RC seems to be equal to 15 seconds. They've told us 15.0. Student repeats the procedure, different values of R. Okay. And it is suggested that there's a relationship here. Sure. And V naught is the initial potential difference across the capacitor, and T is the time over which it's discharged. Yeah, okay. So now when we discharge a capacitor, that's the equation. So I would imagine that the voltage across the resistor is going to be that, because we're going to be subtracting from the total. Yeah? Well, we'll see. The student decides to plot a graph of ln V over V. No. I don't like this note. I don't know why. Ln, do it like this, folks. Ln V slash measured in volts. But lns don't have, I guess I see what they're doing here. It's the ln of the volts, the voltage measured in volts. This is a very clumsy notation. Watch it. I don't like that at all. Okay. So they're going to plot a graph of that on the y-axis against 1 over r on the x-axis to obtain a straight line. Show that the magnitude of the gradient is equal to 15 over c. Okay, well, I mean, we've got... if I do... Oh, unless if what they're doing here is v over v naught. Is that what they're doing, maybe? Is this meant to be the v naught? That's the constant. It's not changing, so it's not italicized, and this variable is italicized. Is that what they're trying to do? Anyway, we'll move it to the opposite side. We're going to take the ln of that, and that's going to mean that on this side we'll get negative t over RC.
Yeah, come on with it. Come on with it. I'm with you. What's up, man? Come here, man. Come on. What's up with that, RC? Too slow for DK. Come on, man. Why you playing, man? RC, leave something for me.
Pretty sure that's a foul, RC.
Now, if we were to graph versus 1 over R, we'll make 1 over R kind of be like our X. And that means that negative T over C is kind of like, this is like our X. Y equals mx is kind of what they are going for here. Time is t. They didn't tell us, so yeah. So it's 15 over. Oh, there's the gradient. 15 over c. We got it.
Just like that, huh?
There's a negative, but I suppose because it's discharging. What's this now? So they give us a table of values. Complete the missing value. Okay. Right. Do they tell us what the initial V is? No, they didn't. So V over V naught. Well, that's what it is. So we do ln. We just need to find the ln of that. That's what they're asking you to put into the table there. So that's pretty straightforward. Ln of this V over V, I get here 1. I have to round it. It's 1.0986. We'll round it to 1.10, and I of course need the plus or minus. So in order to find out the error here, what we need to do is we need to take the ln of the I'll call it the upper limit minus the ln of the lower limit, the lower value, and we'll divide it by 2. So in our case, it'll be ln of 3.2 minus ln of 2.8 over 2. Now, if you do that, you should get the 0.07. I get 0.07. I do have a problem with the formula, is that should be a 5 and not a 6, but hey, maybe they did some rounding. That's okay. Let's scroll on down. I guess it's 1 mark, so you got to have both. So yeah, you know, that's something we don't often see, don't often talk about. Something you do at the beginning of the year and then forget about it, but some exam boards are different than others. Right. I've drawn a line of best fit. They've asked me to plot in the last 2 points. If you I can zoom in here and show you. You, of course, are going to have a nice sharp pencil, maybe even a nice little mechanical pencil. Right, so it's 10 dots, 10 squares to get 2.5. So each of them is a quarter. So that means over here is the 18, and we are at a height of there 1.1. So that's the final point that we just done. And then this is the other one that they gave us, and you can see that my error bars go up 0.2, 0.4, 0.6, 0.7. Okay, and then these ones were because I was at the halfway point here, so 0.2, 0.4, 0.6. Okay. Anyway, I've drawn the line of best fit. It's pretty good. I've got 2 points here. I don't like to have my data, like my slope points within the data set, but it's really close to the edge. There's not much I could do. I did get a nice one here by extending the line all the way through. I suggest you do the same. And so I've done my calculation. You need to remember that your x values are times 10 to the negative 6, and that will give you a rather large number for your gradient. The gradient is equal to 15 over c. I'm just going to drop the negative. That's fine. And we get a value of 2.47, or if you like 2.5, times 10 to the negative 4. Now, if I wanted to, I could change this into 247. We'd make the unit microfarads. I'm just going to put farads here. Okay, we're going to do the error bars in a moment. I just wanted to show it one at a time so it doesn't get too cluttered. Okay, how do I know that the unit is farads? Okay, so here we go. Capacitance. I'll put square brackets around because I want to talk about the unit. According to the time constant at the beginning was 15 seconds. This was inverse ohms, okay, or Siemens. And so when I divide by that, that'll be ohms on top. So I've got seconds per ohm. Now you know that the formula for capacitance is charge per unit volume. You know that volume is equal to current times resistance. We also know that charge is equal to current times time, because a coulomb is how many, the current for a certain number of seconds is how many, coulombs of charge will go by. So the current cancels out. And what are the units of T over R? Well, they are second over ohm. So you could have second over ohm. You could have I think I saw another thing as well, but you see that a second over an ohm is the same thing as a farad, isn't it? Okay, so even though if you don't even need to write farads. If you wanted to just write seconds per ohm or second ohm inverse like that, oops, then you could do that as well. Okay, if you don't mess around with the units, that's okay, but that is equal to a farad, and I'm sure there's some other ways you could describe it as well, but I would say either one of those two is fine. Okay. All right, so I've gone and drawn a couple of things here. I've drawn 2 lines of best fit for the max and min slope. I do want to point out, with my ruler over top of a tablet, I might not be getting exactly halfway in my line of the division here. I know I've gone through that error bar up over here. I noted I haven't gone through here where I've gone through the very edge of the error bar, but I should be actually going through. So my lines are not perfect, but I'm all right, I guess. I got a minimum slope of 2.5 to negative. Oh, sorry, got a minimum slope here, and then I've calculated with it a minimum capacitance of 2.5 times 10 to the negative 4, and I've got a maximum capacitance of 2.2 times 10 to the negative 4. Well, it's the maximum slope which gives a minimum capacitance, right? Minimum slope gives a maximum capacitance. I'm somewhere in the middle. I had noted I had made a mistake earlier, and so my answer is now different than what I just recorded. I ended up getting 2.28. Now, what I did with my maximum slopes, as I converted them to capacitances, I took the average of them, and I divided by 2, and then from this I got the 2.4 times 10 to the negative 4. I subtract that from 2.59. I subtract that from, or subtract 2.21 from the 2.4. My error is 0.2. And the answer is 0.3, but again, my lines are not the best. I'm not exactly going through the error bars like I should, and it's just because I got a marker on a screen with a ruler. I think you could do much better with a pencil. I'm not sure how you want to group this. I don't know if you are told to write them separately like this, but you know, these they don't give you enough room to write your answers down, so just group it how you can. Let's move on to part C. Determine the value of R for which the capacitor charges 10% of its original potential in 15 seconds. Okay, so we're going to have e to the negative t over RC. We're going to have some value out in front. Now, we need to know what R is, and we're going to discharge. So we're going to have the potential difference, going down. And they want to 10% of the original. So when I do V over V naught, as we just saw before, that's going to be 0.1, isn't it? Okay, because that's what we were doing up here with this whole graph. It was V over, I like V over V naught, but I don't know what they're trying to do there. And so we'll do ln of 0.1 equals negative t over RC. Of course, ln of 0.1 is going to be a negative value. We can plug in some values here, 15 seconds, and we'll plug in our capacitance as well. So I'm going to do, ln of 0.1, it's negative 2.3, but I'm going to cancel out that other negative. I'm going to divide by 15 and multiply by 2.28 times 10 to the negative 4. That'll give me 1 over R. So 2.28 times 10 to the negative 4 divided by 15. And then we will do the reciprocal of this. And I get R 2,572. So what are we looking at? 29 kilo ohms, something like that. Yeah, 28. Okay. So they've done, you can do this a bunch of different ways. 0.65, that's some ln number in there. They tell you the 2. So they've rounded a bit. All right, so pretty close on that. Let's go back up to the original part of the question up at the top. Right, so we were supposed to show the gradient was T over C, which is what we did. Okay. We plugged in those points from before. Finally got the uncertainty to go. So here you get 2 points for correctly plotting within 1/2 of a small square, and you get a mark for a line of best fit. Ignore accuracy, length of the error bar, but if it's really bad, you might have some bad slopes and stuff. I think you get error carried forward on that. I'm not sure. And I don't get what this is. Or both worst acceptable lines drawn. I don't know what that means. There's a line of best fit. Okay, so you get a mark for drawing a line of best fit, but I guess if you don't have a line of best fit, but you've drawn the worst acceptable lines, is that your max and min lines? I'm not sure what they mean by this. Worst acceptable straight line drawn. I don't know. But anyway, that's our calculation. We were 2.3. What were we? 2.4? 2.28. So we were actually pretty close. That's pretty good. I don't get a 0.3. I get a 0.2. But again, that's probably due to my slope lines not being the most accurate. So I think you get a picture of how it goes. Pause this and you can read some of the nitty-gritty if you like. All right, this is an Edexcel question from 2017. This is paper 1. We've got, again, a capacitor and a resistor. Okay, describe what happens to the potential difference across the resistor and the potential difference across the capacitor after the switch is closed. Okay, well, let's see. It's an uncharged capacitor. Okay, so its charge, it's the voltage across the capacitor is going to start at 0, and it's going to go up to a maximum, probably 5, I would imagine. And the potential difference across the resistor is probably going to start at 5, and it's probably going to drop on down to 0. Okay? I would imagine that's what's going to happen. So right now it's uncharged. There's nothing going on. When we close the switch, so for 4 marks, when we close the switch, current's going to flow. Okay, some charge is going to collect on the plates. and the charge is going to increase. As the charge increases, the voltage across the capacitor will increase. If the voltage across the capacitor increases, it will decrease across the resistor, and eventually there will be no voltage across the resistor. Okay, it'll all be across the capacitor, and eventually I don't think any current's going to flow. Because it'll be completely charged, and that'll be kind of it. Once the charges have stored up on those plates, nothing's really going to happen. Let's see what we got in the mark scheme. Maybe I could have a few more points in here, but that's basically it. Right, so the PD across the capacitor is going to increase, or across the resistor will decrease. So we said that. We said across it's going to increase to 5 volts for the capacitor. Good. We said the resistor starts at 5. It's going to reduce to 0. I believe we said that. And you could just say it's going to increase or decrease exponentially. So that's pretty good. Try to practice these written word questions. Be eloquent. Kind of explain what's happening in the details. And note that they want to know what's happening to the resistor and across the capacitor. So talk about both. Moving on to part B here. Battery and switch are replaced by a signal generator. Okay, peak differential difference 5 volts. Signal generator has negligible internal resistance, of course. Here we go. Graph of the square wave is this. On the graph, add values to the time axis and sketch a graph of potential difference across the capacitor for 2 cycles of the wave. Okay, well, this is the output of the signal generator. So it's not an alternating in terms of going positive, negative voltage, direction of current. It's a digital kind of thing, and it's either on or off. Okay, so if there's no potential difference, nothing will be happening. Okay, but you know the shape of the curve for a charge. Okay, it increases at a decreasing rate. It's going to increase and level off. Maybe I could make that a little sharper up there. Yeah. So it's going to level off there. Something like that. Make sure they look relatively the same. There we go. I think that's pretty good. Assume the capacitor is initially uncharged. We've done that. Do we need to write something? Add the values to add values to the time. Oh, okay. So 20 hertz. So 20 hertz is 20 waves per second. So the period is going to be 1 over 20. So that's 0.05. So 1 period's 0.05. So I'd say right here 0.05. And this is milliseconds, so we're going to move the decimal over. So that's 50 milliseconds. So we'll say this is 50 and this is 100. So we've added the values of time. Okay, so is that everything? Yeah. Assume it's initially uncharged. Well, if it's initially uncharged, so it's going to charge up, but then when it's off, it'll go on down. It will discharge. Because when it's off, it's kind of like, what's going to happen? Well, it's still connected to that resistor, isn't it? So it will discharge as well. And this will decrease at a decreasing rate. Both are increasing or decreasing at a decreasing rate because the gradient becomes 0 at the end of that part. Right. Okay, so let's see how we've done. So 50 or 100. Yeah, so 100. We figured out 100 milliseconds. We did that. Unit of time constant. We could have put time constants. We could have put I suppose time like an RC and 2 RC. Is that? Oh no! Wait a minute. Oh, did they tell us the capacitance? From up above, way in part. Okay, so part A, they told us the capacitance,
And the resistance, we could have done 100 ohms times 50 microfarads. We could have done it. We could have figured it out in terms of the time constant. A time constant is 0.005 seconds. Okay, so we could have. In half a cycle, there are. Okay, so we could have said 5 time constants. I would have thought just doing milliseconds is fine. But it says use of time constant. Do you need to have that? Didn't get the impression here. That's the time constant. And then half a okay, you do need to, because half a cycle is this is half the number of seconds. So it's 25 milliseconds. So it's 5 time constants. Now, I'm not sure where you would mark that. It doesn't say anywhere that you need to do that. But that's interesting. Time constant. So that's interesting. Anyway, let's move on. Charging curve from 25 to 50, just about reaching 5 as shown. Or whatever you've calculated, and a corresponding discharge curve as we've drawn. Curve should look exponential. Yeah, well, we've done that. So everything's good. I just this use of the time constant just kind of throws me off. I guess it doesn't say anything in here, but be aware that you might have to calculate the time constant. Okay. All right. Next, I've got a Cambridge Pre-U paper from 2017. It's a paper 2. And there's some questions here about internal resistance and a rectifier and AC power. And then we get down here to the capacitor question, part E. Okay. Switch is closed. There's a capacitor and that's it. There is an internal resistance in this question, though. Explain why the current in the cell decreases and eventually falls to 0. Electron, let's see, so this is positive, conventional current. Electrons are moving this way. Electrons are going to build up here. But what's the battery doing? It's like an electron pump. It's going to pull electrons from this plate. Yeah, electrons are going to collect on this side, and it's going to be negatively charged. But it's going to withdraw electrons from one side and move it over, and you're going to build up positives on the other side of the plate. And so once that capacitor is fully charged, the current stops. Okay, that's basically it. So for 3 marks, when the capacitor is fully charged, current stops. Why is this? Well, because electrons aren't going to move anymore. We can see what they say about that. Let's have a look. So part E, voltage across the capacitor increases. Yeah, okay, I didn't mention that, but that's true. The decrease in potential across the resistor reduces the current. Okay. And it's 0 when the 2 potential differences are equal. Well, okay. So they're going it for a little more technical there, aren't they? So yeah, it went to a little bit more detail here. So basically, if you think of this as a potential divider, right? You've got a potential difference across this resistor and across the capacitor. When it increases across the capacitor, it'll decrease across this resistance. This resistor, but the resistor is the one that controls what the current is going to be. And so, there's no resistance out there. It's just little r. And so, this potential difference will increase. So it'll decrease across here, and if it decreases across there, it's got a set internal resistance. The current will decrease. So that's what's happening. That's really what's going on. I guess that's a better answer, isn't it? Okay. So once the 2 potential differences are equal, there's no flow of charge. Okay. So you can look at it mathematically. You can look at it kind of, in an explanation type thing, which I think we've covered it. But again, you want to practice to make sure you get the nuances of your respective exam boards. Let's go on to part II here. The capacitor is discharged. The switch is then closed momentarily for 0.2 milliseconds. Discuss whether this time interval would be sufficiently long to fully discharge the capacitor. Okay, so let's do some calculations. The capacitor is discharged. The switch is then momentarily closed.
is this enough time to fully I'm sorry, did I read that wrong before? To fully charge. Okay, so to fully charge our equation is this, isn't it? Is that enough time? Well, it's the time constant. Time constant, R times C. So we've got 0.54 ohms times 62.5 microfarads. So let's figure out what the time constant is. 0.54 times 62.5 times 10 to the negative 6. I get, and even if we, because the time constant is in seconds, so even if I change my answer to milliseconds, I get 0.8, I guess, milliseconds. So I would say no, the time constant, it's 3 marks here. I would say the time constant is larger than the 0.2 milliseconds. So I would say no. Q, capacitance times the voltage. 1.24 times 62.5. So if you multiply these values they give you at the beginning, you get 7.75 times 10 to the negative 5 coulombs. Now, is that what they're doing in the mark scheme? Is that what that 7 point? So they get a slightly different number. Yeah, I see. So this is the fully charged. And now they want us to calculate this. Okay, so I'm just going to do this calculation below. I'm going to do V. V naught is 1.4. I'll do 1 minus, now I've got E. So this is 0.2. That's milliseconds. Divided by 0.03375. Also milliseconds. I do 0.2 divided by that. I get 5.9. So e to the negative 5.9259 kind of repeats. 925, 925, 925. Anyways, if I do e to the negative of that, subtracted from 1, I get 99.7. Huh. See, you might look at this linearly and say, oh, but I mean, oh, 0.2. Oh, wait a minute. I think I totally made a mistake before. When I read this before, I thought, oh, I've got 0.3. I've got 0.2 out of 0.33, and I thought, oh, it's only 2/3 charge. But no. This is you know, how many time constants are going to happen in 0.2, and that's what they're doing in the mark scheme here. They're saying, hey, look, you know, the time needed is 6 time constants. So there we go. Or you could pop in some numbers and calculate it. So and then you come to the right conclusion. Okay. I misread that number there, didn't I? Okay, wow. A whole decimal point makes a huge difference.
I must have put a decimal point in the wrong place or something. I always do that. I always mess up some mundane detail. Oh! Well, this is not a mundane detail, Michael!
Be careful for that. Okay, this is a Cambridge Pre-U Paper 3 from 2018. Right, so there's questions about how the charge is distributed on a plate. I don't want to go through all the basics. I want to go only through stuff not covered in the Irish curriculum videos. Calculate the charge. Yeah, we know. We can quickly go through. Let's just quickly go through some of these. What are they asking here? Explain why it's necessary to know the internal resistance of the battery when calculating the charge. Well, because the internal resistance is going to affect what's happening about like what the current is going to be, won't it? What do they say here? The rate of charging will vary with internal resistance. Internal resistance only affects the rate or time of charging. When fully charged, the current is 0. There will be no lost volts. So it just affects the time. The final charge only depends on the EMF. Okay, so final charge depends on EMF. The time of the charge depends on the internal resistance. Okay, there's some energy calculations. I'll leave that to you because I think that's done elsewhere. Capacitor, time taken for the change in this capacitor to decrease. Okay, so this could be interesting. Let's do this one. So it's going to discharge, and we're going to start at 68. We're going to go to 18. This, of course, is times 10 to the negative 6, times 10 to the negative 6 microcoulombs. It's discharging, so it's going to be times e to the negative t over RC. We'll have to figure out what, there's our time constant. So RC is equal to the kilo times the micro is going to leave it to a times 10 to the negative 3. So 3.8 times 47. So 178.6 times 10 to the negative 3. Or if you like, 0.1786 seconds. So we'll put that in there, the time needed for this. Okay, Q equals Q naught times e to the blah, blah, blah. If I do the ln of each side, so take the ln of e to the negative whatever, that just gives me minus t over RC. So now I can subtract that over. Okay, and if I subtract that over, that's the same thing as saying ln of Q over Q naught, isn't it? Okay, so that's probably better. Because the Q is less, right? And anyways, that's equal to T over this this stuff, right? Now that's still negative. If I take the okay, and now our 10 to the negative 6 is going to cancel out as well, isn't it? So
Thank you!
18 divided by 68. Okay, so it's a 0.26 something, so I'll do ln of that. I get a negative 1.329. I'll multiply that by a negative 0.1786. I'll get a positive t, and when I do that, I get, is that 0.2, let's say 0.24 seconds. Right, good, lovely. So doing the log stuff first, doing this ln stuff first can be quite helpful, actually. In fact, I might go so far as to say, hey, rearrange the whole thing first. So we're kind of out to here. If you wanted to, you could say, hey, T is going to be equal to RC times ln Q over Q naught. And I think, boom, just plug all the numbers in and you'll get it in one shot. So that's good. If you do it bit by bit with numbers plugged in, you might get some negative issues, okay? But it's just easier. You don't have to type in this times 10 to the negative 6 stuff in your calculator. It's just easier. Okay, alternating voltage supply connected across a capacitor. So in this question, we do actually have it going from positive to negative. What do they want us to do here? The variation in alternating voltage is shown. The resistance of the supply can be considered to be 0. Okay. Use the same time scale. Sketch the graph to show how the charge of the capacitor varies with time. Mark on the vertical axis. Okay, in terms of capacitance, energy. What is this? Frequency? Well, we'll have to mark off our graph here, a maximum and a minimum. So the maximum charge will be when the current is a maximum, and the minimum charge will be when the current is a minimum. And when there's no voltage, it will have discharged. So I'm assuming it's going to charge up and then discharge, and then it'll be in the opposite direction, so it'll charge up in the negative way and then discharge. So I guess it's going to follow the alternating voltage, which I guess makes sense. I would label this, I don't know, max charge, Q max, something like that. All right, we'll go on to what they want us to do with
Sketch a graph on figure C to show how the current in the circuit varies with time. Deduce an expression in terms of C, E, and F for the peak current and mark on the vertical axis. Okay, so same type thing. Right, now I seem to recall that current graphs always are in a bit of a delay from the voltage. Capacitance is charge over voltage. Charge is capacitance times voltage. They're not using voltage, they're using E. That's what they meant by C and E. C, E, max? Max? I don't know, this one's negative. What's going on with the current? Well, if the charge is building up, it's like this. If the charge on the capacitor is maximum, then the current is going to be 0 at those points. Okay? Here the plates are just switched polarities, but it's still going to be 0. And the part at which when the charge is 0 is when the current is going to be moving the fastest. So I would max out the current, and it looks to me like you'll get a cos curve instead of a sine curve. And how are we going to label let's see, what are they doing with where do we label the frequency?
What's the frequency?
Frequency is 1 over the period. The period is the time for one cycle. Current. Oh, I see. Current is equal to charge per unit time. So they want us here. I guess we're labeling the unit. Is this meant to be a unit thing for this? So the current here isn't going to be Q. It'll be C over V per unit time. But per unit time is the frequency. So is it a CVF? Because frequency is per second. So not a V. So a C E little f, max and min, CEF. I'm not sure if they want CEF as the units or what they say on the vertical axis for peak current, and mark this on the vertical axis. Deduce an expression in terms. Yeah, so we've done that and mark. Well, we've marked it, but there's our expression. We've done that. We've done that here, I guess. And the last one here, sketch a graph on the D diagram to show how energy is stored in the capacitor. Mark on the vertical expression. Right. There are times when the energy stored is decreasing. Describes it. Okay, all right. So we'll answer that in a sec. All right. So voltage or potential difference is measured as energy per unit charge. Now I gotta be careful with the E because they're using the E as EMF. So E is EMF. Let's use U for energy. U is E times Q. But of course Q is that's the charge. Charge is capacitance times voltage. Oops. Capacitance times EMF. And I believe the energy equation is it would be like a half CE squared typically. So I don't know if they want, because it's half CV squared usually, isn't it? Do they want the half or just the because we've done that here again. But you know, max energy, min energy, max, min. So we got our expression. Yeah, that's what it's going to need to be. How's this graph going to look? I think the energy being squared, or this potential being squared, is going to make it higher. But I have a funny feeling something else is going to happen. I'm going to... Let's just consult the mark scheme, because this one's a bit... right. So it's a sine squared curve. Yeah. So it's proportional to this, right? But it's that potential value squared. So when you square a sine graph, it becomes sharper, doesn't it? Kind of peaks go up. So the frequency twice that of the frequency of the charge is what they say.
So whatever we had for charge, we want it twice that, don't we? So we want it to go like this. A very poorly drawn sinusoidal curve, but there we go. And I suppose there's some calculus involved. Let's see. Gradient here is 0. Gradient here is 0. That's the value on the graph here. Wherever the gradient is 0, 0. Yeah, and then we have this is another inflection point. So there's some calculus involved, but you don't need to do that, do you? There's times when the energy stored is decreasing. To describe what's happening, let's see what they say. The capacitor is discharging at these times. No energy is dissipated. Current and voltage are out of phase. At these times, energy will be returned to the supply. Okay, interesting. Yeah, so we know voltage and current are out of phase. Look, some of you don't get into this alternating voltage stuff in your curriculum. Some of you do. So this can get quite hairy, actually. Okay. Did I get the expressions? Did I get everything that they needed here? So marked CE on the axis, correct position and correct. Well, we got the correct graph. We put CE, I guess. Yeah. Okay. C times the voltage is the charge. Yeah, okay, we got a cosine curve here. Okay, so if they want you to incorporate the frequency, it's not, what did I do? Instead of just saying CEF, they want you to say CE, and then how does it vary in terms of F? The F is the frequency. We know that it's going to be 2 pi. We'll put frequency and then the time, because your sine argument, the argument of a sine function needs to be, of an operation needs to be unitless. So your frequency and time, the units cancel. And then, if you take the derivative of that sine curve, you get a cos curve and you get a factor of 2 pi f out front. And that's where I would have had, I didn't have the sinusoidal bit, but my f is out front. I am off by a factor of 2 pi though. So peak current is CE 2 pi f. And you need that in order to properly label what value that is there. Okay, so that's where that comes from. You need to use the trigonometry. It's not that simple. Again, some exam boards will do this alternating current stuff, others won't. Okay, the rest of this I think we've covered. Bit of a tricky one. Okay, and moving on here, I've got a paper 3 from, again, Cambridge Pre-U. This is from 2019, so fairly recent. Define capacitance. I would define it as charge per unit voltage, or charge per unit potential difference, something like that. Let's move on here. So we've got a circuit. Tell us the capacitance, 40 microfarads, two-way switch. So this capacitor is going to charge when the switch is closed on X, and when we close it on Y, it's going to discharge through the resistor. There's an internal resistance there, because of course you need there to be a resistance. The time constant of the charging circuit is the same as the time constant for the capacitor discharging through a 10 ohm resistor. So what's the time constant of the charging circuit? Well, 40 times 10 is 4 times 10 to the 2, and it's microfarads, so that's going to make it 4 times 10 to the negative 4.
You're amazing. You figured this all out already.
And let's see, the capacitor can be considered to be fully charged after charging for 10 seconds. So just a reason to explain this with reference to our answer up above here. Well, the time constant is 10 seconds, and that's a small amount of time. How many times would you say that goes in? 0.1 divided by my answer, I get 250. So that's 250 time constants will have passed in the tenth of a second. So I'd say that's more than enough time to be fully charged. Let's move on. Okay, so there's a question here. We need to fill in the table. I've gone ahead and calculated the ln of the current in milliamps, and there we have the values. Complete the table. We've done that. Plot a graph. of the ln of I versus t, draw a best fit line. So I've done that graph. I think I've done a fairly good straight line with my fine pen and ruler over the laptop surface. And let's just see. I think I need to calculate a gradient or something probably. So use my graph to determine the current in the discharge circuit at time equals 0, right? Yeah, so see, at time equals 0, I got here, I didn't quite extend that line, but I'd say it's probably about half. So let's see, that's I'd say it's 0.515. If I have the ln of the current here, I need to do e to the power of that ln of 515, and it's actually a negative, isn't it?
Sorry, Hans, wrong guess. Would you like to go for double jeopardy where the scores can really change?
Ln I naught is equal to 0.515. If I do e to the ln, yeah, okay. So that'll give me I naught, and I'll do e to the 5.5. Yeah, this is interesting. It's the ln of the current, and I'm getting a e to the negative 0.515. Ah, there we go. I didn't have a negative. Yeah, so that needs to be a negative there, because it is. Right, so I had done that correctly, right? So that's a negative. So e to the negative 0.515, and that will give you, I've got 0.597, so yeah, we'll say that's 0.60, fine with me, good. Okay. The time constant of the discharge circuit. Well, the time constant of it's said up here, the time constant of the charging is the same as a constant for the capacitor discharging through a 10 ohm resistor. So, yeah. Are we to assume that R there is 10 as well? It's probably a gradient calculation, isn't it? Here's the resistance. Yeah, so time constant, because I think you'll recall if I do ln of V over V naught, that'll be equal to 1, well, it'll be equal to negative 1 over RC times time, time being the x variable. So our gradient is going to be the time. So if I want the time constant, it's 1 over m, negative 1 over m. So we need to calculate the gradient here. Alright, so I found some nice little points here along my graph. This one's right on the crosshairs. That's a good one. So that's 0.02, 0.54, and then one down here just before the other point, 0.62, negative 1.26, and so I calculate my gradient to be negative 1.2. RC, of course, is the negative of that, so 1.2 is the same as 6 over 5, so I get 5/6, or in other words, I'm going to get a time constant of 0.83 repeated, or just 0.83. Okay, I'm not sure about the rounding on here, because the answers seem to be rounded. Now, I think if I look at my graph, I probably, I've got two that are just slightly on the side of the line there. So if I were to have drawn just a slightly more shallow slope there, if I had been up a little bit, but see, all the other points go right through the line, so I'm kind of happy with that line. But I could see maybe my gradient is maybe a bit high. But if my gradient's high, that means my time constant, if I make my gradient lower, it means my time constant would be higher. So I'm actually not going to get close to the 0.8 that they have. But anyway, maybe they've rounded down. Look at your example for the rounding rules. So if I've got my time constant, then I'm just going to divide that by the capacitance, and I get about 21 kilo ohms, or 20.8 ohms. And the electromotive force of the battery should be equal to I naught times the R, so we can just multiply those two values. So if I've got my answer from here times 0.6, then I get 12,000. Oh, that seems a bit high. But wait, milliamps times kilo ohms. Yeah, and if I do that, yeah, I mean, I'm just moving the decimal place over, aren't I? Because kilo ohms will cancel out with milliamps, and I got 12.5 volts. All right, that's a 13 marker. Let's look at the answers. Right, so definition, charge over voltage, sure, we got the right time there, that's fine. 250 time constant's worth, or 10 seconds is way, way larger than the time constant, good enough. All of those were my values for the table, I believe. And all 6 points plotted correctly, yes, and I got a best fitting line, I would imagine. Let's just see how the rest went. Yeah, so we understand why I got the 0.6 now, okay? So it's the e to the negative 0.15. It's e to the negative I-intercept or y-intercept that you get there. So they got 0.8, like I said. I got 0.833. That's pretty close. You divide and you get 20 kilo ohms. I had 20.8, so that's not too bad. And you multiply those two values and they get 12 volts, which is, yeah, 12-volt battery. Makes sense. I got 12.5. Doesn't say anything here about errors carried forward. So I'm not sure how the Cambridge PU is going to handle that, but I was fairly close. Again, I don't know if that has to do with the rounding, if they're just rounding down to the, to the nearest hundredth. So the 3 rounds down instead of 8.3 repeated, it's 0.80. That could be it, but check with your exam board about that. Okay, and this is a WJEC 2018. This is a Unit 4 paper. What I'm interested in is part B of the question here. So a group of students investigated charging a capacitor. Here's your graph. Here's how it should look. Practice drawing these. Draw a circuit diagram of the apparatus that might be used to obtain the data. Right, so for the diagram, we're just charging a capacitor through a resistor. All right. So we'll get a cell, and we'll have, say, a resistor. Oh, let's try to be a little neater here. Ugh. So have a resistor. It might be wise to bring a ruler and draw these things with a ruler. And we'll have a capacitor here. And I suppose somewhere along the way we'll need an ammeter, so we'll do that. And we are looking at the PD across the capacitor, so probably we need a voltmeter too. So I'd say something like that. Use the graphs to determine the EMF of the power supply, the resistance, and the capacitance of the capacitor. Okay, well, the EMF of the power supply, it's going to max out at 12 volts because that's the highest that it can get across the capacitor. And when it's that high across the capacitor, then it'll be equal to what it is for the cell, and there'll be zero potential difference across the resistor, because the resistance is equal to I times R, and R is constant for the resistor, but the current's going to change, and the current will reach zero as the capacitor charges. As we see here, the current's going to go down to zero, so that'll be zero. So these PDs need to be equal, don't they? And so the resistance of the resistor, well, let's see. The starting current, the initial current, I naught, appears to be equal to 2.7 milliamps. And if the potential is 12, then I would say 2.7 milliamps. I'm going to drop the milli, 12 divided by 2.7 R, so that's 4.4 kilo ohms, I'm going to say. And the capacitance of the capacitor. You need to look at the graph. How long does it take to go down to 30% or what? I suppose maybe it's easier to do the 12. Either way, you need to take a certain percentage. And you just need to know this. I'm guessing you read that off the graph. So what's 37% of the 2.7? What you need to know from your decay graph, you know that when t is equal to RC, when the time is equal to the value of the time constant, you will be down to 37% of your original value. 37%
of 2.7 is 0.999. So we're just barely at 1. I'm going to zoom in here. Come on. Right. Oh, yeah. So 0.99, we're practically at 1. And if we're practically at 1, that's just a little bit below 8. But we can say it's approximately 8 seconds. I suppose if you were to take 63% of 12, 63% of 12 is going to give you 7.56. So 6.4, 6.8, 7.2, 7.6. It's very close to 7.6. And if we look at that right down there, there you go, 8 seconds. So since the time constant is 8 seconds, we now take 8 seconds and divide by that value. And when we do that, we get 1.8 times 10 to the negative 3. That's the farads. That's the capacitance. So 1.8 millifarads. Right. Capacitor in series with resistor and some sort of power source or cell or battery, properly placed ammeter and voltmeter. I think we've done that. That's great. Voltmeter across the capacitor, because that's what they told us. It's the PD across the capacitor. What else on our calculations? We got 12. You get 1 mark for saying that 12 stated. Well, we got it from the graph. So 1 mark. Yeah, 1 mark for that. And we've divided to get, yeah, so there's the current. Again, off the graph, we divided to get the resistance. With incompatible voltage, and I did no. Okay, so something about you can't get the second or third marks if you don't have I's and V's that match up here. And then our constant, and there we have it, yeah. Okay. Or taking logs and rearranging. Yeah, you could have done it that way. Alternative, EMF is 12. We've done that. Find dV/dt and I at given time. Okay, yeah. At a given time. So let's say at the 10-second mark, find out what the current is and find out the rate of change of voltage. Okay, why are we doing that? Well, because capacitance is charge per unit voltage. Charge is current times time. And there's your voltage. So if you want the capacitance, you're going to take the current at a certain time t, and you're going to divide by dV/dt at that same amount of time. Because dV/dt, when you do the reciprocal and you divide, you're going to get t up on top. So yeah, you could do it that way. I think that's what they've done. Then they divide then. Yeah, so here at 10 seconds, hence calculate, yeah, current is equal to C times dV/dt. Not, yeah, so the capacity, yeah, and then we rearrange, which is what we've just done. So you get 1.8. Yeah, okay, interesting. And then from there, use your time constants, knowing the value for the Imax, 37% of Imax on the discharge, or 63% of the Vmax on the charge, and work backwards and find your resistance from the time constant, and there's your resistance. So there we go, and you need to have the proper units. Okay, so that's an interesting way of looking at it. Knowing your units will really pay off. This is an excellent question because it really gets you to think, well, what would that do? And you could try it out. Do it at 20 or I don't know, 35 second. Well, maybe not 35, but 20 or maybe 25. Find the gradient at that time. Find the current at that time, and either way, you should get the same results every time. Great way to practice when you're practicing for your past papers. I wouldn't do it 2 different ways on your test. You won't have time. But definitely great thing to practice. What a lovely question. Well, this is an A2 Unit 4. This is WJEC. This is the fields and options. So charged 8 nanofarad capacitor is discharged. Okay, calculate the resistance of the resistor if the time constant
is 15.5 milliseconds. Okay. Calculate the resistance of the... Oh, well, that's pretty straightforward. So 15.5 times 10 to the negative 3 divided by 8 times 10 to the negative 9. I get 1.9 mega ohms. Does that seem a bit high? No, 1.94 mega ohms. Okay. Normally we don't see resistors that big, but there you go. Calculate the fraction of the initial charge remaining in the capacitor after 31 milliseconds. Okay, well, 31 milliseconds, that's 2 time constants. I don't know if we've got a symbol for time constants. Yeah, I got, because with half-life it's t sub 1/2, but I don't know what we do for time constants, but it's 2. So let's see, we're going to have, if it's being discharged, it's going to be 37% of the original amount. So 0.37 squared, I'm going to say, probably 0.37 times 0.37. So 0.1369. I don't know if they want that as an actual fraction, but there we have. Now, it's 3 marks. What else are they looking for? 2 time constants interpreted. Yep. Okay. Or we could substitute into the equation if we wanted. 0.37 squared, or rearrangement of the equation. And there we go. Now, we gave an answer. Okay, so they get 13.5. Why do I get 13.69? They get 13.5. That seems a bit weird. If you get 0.37 squared, you won't have that. And you can actually break that down into an equation if you want. If you wanted to, you could do this as Q, or you can do it as I, because it's Q is just I times T. But we'll do it So what do we get? If we were to have plugged in this here, we're going to get e to the negative 2. So e to the negative 2. Oh, I see. So there we go. E to the negative 2 that's equal to Q over Q. E to the negative 2 is 0.135, and there you go. There's your 13.5%. So that's why I get 13.69 and they get 13.5. There you go. And we wrote down, hey, that's 2 time constants, and we got a mark for that, didn't we? Right here. So that's good. I see that there's a question C. Okay, so we've got the identical 8 nanofarad capacitor. It's being charged. Same resistor as up above. What was the resistance we calculated? 1.94 mega ohms. Okay. And now what? Without further calculations, sketch graphs of the charge on the plates of the capacitor against time. So we're going to charge up the capacitor so we know that it's going to, the current is going to lower. It's going to have that exponential drop there. Now they've marked it off for us Q naught over 2. We don't really deal with half-lives of the current here. We tend to deal with the 37% stuff, don't we? Okay. Now 40 milliseconds. Are we still doing time constant of 15.5? Same large resistor, same capacitance. Time constant is still TC. Time constant is still 15.5 milliseconds. So I'm not sure where it's supposed to be a half, but I would say it needs to go something like that. Charge. Oh, I'm sorry. This is the current. So the charge, but we know that it should go Something like that. Correct shape starting from 0, increasing with decreasing gradient, 1 mark. Yes. 50 to 75% charged at 1 time constant, or what's this? 8 to 15 milliseconds in half-life. Oh, okay. It's an 8 to 15 millisecond half-life. Right. It would be interesting to do the half-life, wouldn't it? Or see if that's a half. Ln of a half, that's that negative 0.693, and then times RC. We know what the RC is. It's milliseconds. It's the 15.5. So we'll take that number times 15.5, and I get, for a half-life, I get 10.7. I guess milliseconds. So they say between 8 and 15. It's just a graph. Of course, dudes, they say without any further calculations. So you wouldn't be able to do this or check this. You just have to kind of have a feeling for it. My blue line was all right, but I think it was a little too kind of dented in. This is a pretty zoomed in graph, so yeah, there we go. But I think 50 to 75% charged at that time of the, because you know, for the here we are, this is the time here for yeah, and I'm at 75% for my time constant after 1 time constant, so that's fine. That's what we want, okay? And I'm imagining it's the same thing. Maybe my graph is not exact. Correct shape. So we start at I naught, and then what's this? 0. Decreasing and decreasing negative grade. Starting from I naught, and then I think it should say going to 0. Oh, I see. That's the point. I naught 0 on the graph. I naught 0. Shouldn't it be 0 I naught? Shouldn't the x coordinate come first? That's not good for the mark scheme. I don't like that. We start at 0 I naught. That should be the coordinate that we start at. And then we decrease at a decreasing rate. And here we need to have 50 to 75% discharge by the time we've got 1 time constant, or again a half-life. So the time constant is here, and I'd say we're between 50 and 75% discharged. Well done. It was a close one. If I had drawn it any more kind of curved in, that could have been a problem. So I got it just shallow enough, didn't I? Okay. And the half-life, they say again between 18 and 15 seconds. So here, 8 to 15. It's kind of close. It's kind of close. This is not the best curve. It's all right. I got the marks. I hope you get them too.
Okay. Time circuit's on. Flux capacitor. Fluxing. Engine running. All right.
Okay, and finally we've got an AQA. This is a paper 2, physics, and it's from 2017. Just we'll finish off with some multiple choice questions here. Again, I'm not going to look at plate separation and that sort of stuff. Here we go. It's going to charge and then discharge. What fraction of the original remains on the capacitor? 4.8 seconds. Okay, so we'll calculate the time constant here. I get 2.4 seconds for my time constant, and they're telling us this is 2 time constants later. Okay, so if it's going to discharge, and we've got 2 time constants later. Okay, so if it's charged, it's fully charged. So we'll discharge it. So we're at 3. Oh, okay, yeah, it's the 0.37 squared again, isn't it? So I'd say A, because it's 0.37 squared. A, yeah, that's yeah. So it's 13.69 or. So we'll check our answers. 21. The answer is A, and we've done it.
Okay, and there we go. That takes us up to the end. Remember that this is a video which is meant to supplement what is already on the iRevise site. Okay, so thank you very much, and we'll see you in the next video.